Howdy, and welcome to lecture number 9 of Mean 315 Thermodynamics. Okay, so before we get started, let me just give you a couple of announcements here. So first thing to note is that homework number 4 is due on Tuesday, September 25th by 12:45 p.m. in 104B Zachary, and Miss Jessica White will be there waiting to collect the homework from you. So even though we don't have class on that day, that's what this lecture, this online lecture is taking the place of, you still need to submit your homework number 4. Homework number 5 will be posted on e-learning by this time as well. Second reminder, your participation assessment for the next lecture for lecture number 10 on Thursday, September 27th, will be graded. Okay, so this is a graded lecture, and the concepts that you'll be assessed on are going to be highlighted in this lecture. Okay, so what are we going to be talking about today? Well, let me just kind of quickly summarize where we're at in terms of our discussion so far. We basically have transitioned into studying properties, as you know, and it's kind of helpful to reflect on exactly what we're going to be looking at, what types of substances we're going to be looking at this semester. We're basically going to be looking at 3 major classes of substances. The first we've already studied, and those are what we call phase change substances. So something like water, which has a phase change, has the saturation dome, for example, undergoes a phase change. We're going to study that extensively. And we'll study R134A, which is also a phase change substance. In other words, we can have the two-phase mixture. Because these are phase change substances, these two substances have their own special tables, right? So water, for example, has table A4 and A5, A6, A7, and A8. And R134A has tables 11, 12, and 13. The reason why they have their own special tables is because we need to be able to capture that information during the phase change process. And so we have to have as much information in that as we possibly can. The second major class of substances that we study are ideal gases, and this is what we're going to study extensively today. That's why we have the 2 asterisks identified there. We'll get into that in just a moment. The third major class of substances that we're going to use are liquids and solids. We're going to study this a lot less than we do either phase change substances or ideal gases, but all the same, it'll be important for us to know how to work with liquids and solids. We're not going to really study these extensively until we study closed system analysis, and that's going to come after we do open system analysis. So when we're done talking about properties, we're then going to go back to studying open systems, things like turbines and compressors and heat exchangers. And then once we're done with that, then we'll do closed system analysis, in which case a liquid or a solid can effectively be studied as a closed system analysis. The one exception to this is the one exception to the study of the liquids is when we make the saturated liquid approximation. So sometimes we'll have a substance which is a liquid, but we don't. It's not at a. During the process it doesn't stay a liquid, and we don't have properties, or we don't have an entry for its state in the compressed liquid table, table A7 basically. And when this happens, we have to make the saturated liquid approximation. And this is described more deeply for you in the auxiliary lecture on using tables. And if you don't want to watch that auxiliary lecture, you can read about it in your textbook. Oops, I've gotten somehow I got out of line here. Let me fix this. So I give an example on how you do that in the auxiliary lecture, and then it's also described in your textbook. Okay, so today we're going to talk about ideal gases. So let's go ahead and define what an ideal gas is. And you've already come up with this definition before in your homework number 2, I believe it was, where basically an ideal gas is one which has a sufficiently low density such that the particles behave independently. So in terms of microscale energy, right, remember we had 3 types of microscale energy that we talked about. We said there was molecular kinetic energy. We said that there was intermolecular energy. This would also be the same as molecular potential energy. And then the third type is the intramolecular energy, and that's capturing all of the energy that happens among atoms that are composing a molecule or among particles that are composing an atom. So in terms of microscale energy, when we talk about ideal gases, it means that they have negligible intermolecular energy. In other words, you don't have that molecule-to-molecule interaction, which is what's captured by the molecular potential energy. So because of this, because you don't have that intermolecular energy mode, ideal gases have, let me just do the little grammatical correction here. Sorry about that. They have consistent behavior, which can be modeled very easily, right? So we have essentially a model, and you're all familiar with this model. It's PV equals nRT. We'll get to that in just a moment. But they have very consistent behavior that we can easily model, and they have consistent behavior in terms of how their energy changes during a process, how their entropy changes during a process. All of those important things, and we will get to that later on today. Okay, so now there's a few things in this definition that we need to pay close attention to, right? And one of these is this statement that ideal gases have sufficiently low density. Well, what does that mean, right? I mean, that, how do we know when a gas has sufficiently low density? So for example, the air that we breathe, right? Well, that's a gas. Does that have sufficiently low density such that we could assume it's an ideal gas? What about steam? When we boil water and we have this little vapor cloud that's coming up from the pot of water, that has a lower density than the liquid water. Does it have the sufficiently low density that we need it to have to satisfy this definition of an ideal gas? Well, let's find out how we can provide a more concrete definition to what we mean by ideal gas. Okay, and how we do this is we basically can interpret this on, say for example, a TS diagram or a PS diagram. It doesn't really matter what's on the Y or the X axis in this figure here in the top. But if this is our two-phase region, right? We know that this is the two-phase region. Well, if we're changing phase, then it's not appropriate to assume ideal gas, right? So the first qualification is that we have to have a gas, right? So if you're in this region here, you're not going to be able to make the assumption, right, that this is not, or what we would say, non-ideal gas behavior. Okay, so this would be non-ideal gas behavior in here. And of course, that's also true here, right? This is the liquid region. Well, it's ideal gas behavior. It's not ideal liquid behavior, right? So it's not appropriate to assume it if you have a liquid. And of course, down here is when you get to basically your solid region, right? So if we get very, very close, I have to be careful here. So if we get very, very close to this axis, right, this is basically where we have the solid phase of our substance. Well, again, it's ideal gas behavior. It's not ideal solid behavior. And so we can't assume ideal gas behavior if our substance is a solid. So now let's suppose that we're right in this region here, right? Let's suppose that we're a saturated vapor, or we're kind of in this this region that's close to the two-phase region. Well, here, in this region here, it's very, very approximate, right? So it's not perfectly ideal gas. So we have that it's not perfectly ideal gas behavior, but a reasonable approximation. So you could actually apply ideal gas laws to this region of a substance, right? It's not going to be exact. It's not going to be perfectly correct, but it's still, a reasonable approximation, right? So if you have steam, for example, and your steam never undergoes phase change during a process, well, if you assume ideal gas behavior, it's actually not going to be that far off, right? It might be, say, 20% off in terms of what the accuracy of the number is. So where we definitely can assume ideal gas behavior is up here in this sort of stratosphere region of the TS plane, right? So this is where you have, for example, either very low pressures, right? Remember that the line of constant pressure, so if this is a very low pressure here, right, that line of constant pressure, kind of cuts through here and then rises all the way up. Well, this is a very low pressure here. And as you know, things that are at low pressure have have low densities. Okay. It's also the high temperature region, right? So you have very high temperatures. So if this were, for example, so now I'm actually imposing, what kind of diagram this is, right? So if this is T, well, this is where you have high temperatures, right? Not low temperatures. And so this region here that I drew the circle is where we can basically make very good approximation assuming ideal gas behavior, right? Now you'll notice I said very good approximation. Nothing is ever a perfect ideal gas, right? You'll never get to the situation where you have complete independence of particles composing a system, but it gets very, very close to ideal, such that in our mathematics we really can't see any issues with assuming ideal gas behavior. Okay, so you'll also note basically on this diagram that I drew down here, right? If we were looking at an ideal gas, where would the saturation region of that ideal gas be? It would basically be way down here, close to the ordinates, right? Close to the ordinates. So this is the basic idea of ideal gas, is that you're way out in this very low pressure, very high temperature regime of the TS or the PS diagrams. Okay, so now that's still, so that gives us a conceptual idea of where the ideal gases are, but it's still, again, if I give you a substance and I tell you what its pressure and temperature are, and I ask you, can I assume this is an ideal gas? Well, is there a mathematical way for us to quantify that? And fortunately there is, right? So the way that we can, basically answer the question, how do we know if a substance can be modeled as an ideal gas? The best way that we can do this is with the critical properties, right? So let me just back up a moment, right? So recall that the tip of this saturation dome, that's the critical point. Okay, so that gives us a very clear idea as to where the saturation region is relative to the properties of our substance. So let's suppose that our substance, let's say that the state of our substance is that dot right there, right? That, say temperature entropy is given by that dot right there. Well, by knowing that our properties are here, the critical point locates this saturation dome force relative to that point, regardless of what the substance is, right? And so I can basically look at my properties at this point compared to the properties of the substance's critical point and make an assessment as to how far this point is away from the critical point, and therefore tell me how much of an ideal gas I am or not. Okay? Okay, so we have some ways that we go about doing that. And we define something called the relative temperature and the relative pressure. Okay, so these two are respectively defined as follows. The relative temperature, which we use the capital T subscripted with the letter R, okay, to stand for relative. Well, this is equal to the temperature of the substance divided by its critical temperature. Okay, and just as a caveat, remember we're doing a division here, right? So you have to use absolute temperatures. Okay, and the critical pressure is defined in the same way. Right? So the critical pressure, we use the letter P for pressure, subscripted with R. That's the relative pressure. This is equal to the pressure of the substance divided by the critical pressure. And of course, you have to use absolute values here too, but pressure is generally, we generally think of pressure as being the absolute pressure as opposed to the gauge pressure, for example. But let me just to be consistent, we'll just go ahead and say that we need to make sure that we use the absolute pressure. Not gauge. Okay. Okay, so now we have these two definitions, relative temperature and relative pressure, but how do we, how do I use this information? Well, we have a rule of thumb, okay? And the rule of thumb is as follows. For very high relative temperatures, okay, and again, what does very high mean? Well, now we can actually attach a number. For relative temperatures greater than 2, so if the temperature of your substance is twice the critical temperature, okay, or for very low pressures, okay, and again, what does very low pressure mean? Well, in this case, we would say for a relative pressure less than 0.1, okay, so take note here. Ideal gas behavior is much more sensitive to pressure than it is to temperature, right? So for very low pressures, the relative or the pressure of the substance has to basically be an order of magnitude less than the critical pressure. So if we satisfy either or of these two conditions for very high relative temperature or for very low pressures, then we can assume ideal gas behavior. Okay. Now, the thing is that we may have a combination of the two, right? So, in other words, if you satisfy one or the other condition, right? TR greater than 2, PR less than 0.1, if they don't, it doesn't, they don't both have to be satisfied. It's just one or the other has to be satisfied. Then you can assume ideal gas behavior. But what happens if you're somewhere in between, right? What if, for example, your relative temperature is 1.5 and your relative pressure is, say, for example, 0.5? What do you do then? Is that close enough where it could be ideal gas behavior, right? So, what if TR were equal to 1.5 and maybe PR is equal to 0.5, is that an ideal gas? And to answer that question, we have to get into something called compressibility, the compressibility factor, okay? And we're not going to spend any time on this because, you know, if we weren't behaving as an ideal gas, then you really can't apply any of the rules that we can use with ideal gases. We then have to go into what we call real gas behavior, and that's an advanced topic that we teach our graduate students. We don't teach that at the undergraduate level. But all the same, I want you all to know that you know, if you don't satisfy this one or the other of this rule of thumb of TR greater than 2 and PR less than 0.1, but you're still, you know, wondering if you can assume ideal gas behavior, you then have to go to compressibility analysis and make an assessment that way. Okay, I'm not going to get more into it than that. But if you were to ever encounter that, you can go to your thermo textbook and it describes compressibility. And then a more advanced thermo textbook will describe real gas behavior. So if you find out that you're, you know, based on your compressibility factor analysis, you can't assume ideal gas behavior, then you have to apply real gas rules, and then you have to go to a more advanced thermotext to be able to do that. Where this could come up in your career is if you're dealing with oil and gas, hydrocarbons. Hydrocarbons can very often, so if you're drilling natural gas out of the ground, sometimes that can be very, very close to saturation two-phase region, in which case you have to use real gas behavior. And so if you happen to encounter that, then be mindful of that if you're, for example, designing a pump to pump hydrocarbons that are being pumped out as gaseous phase out of the ground, or something like that. So it does happen quite a bit in the oil and gas industry. Okay, so but for this semester, for now, what you need to know is remember this rule of thumb, right? That TR needs to be greater than 2 and PR needs to be less than 1, either or, right? It's an either or thing. If you satisfy one of these two conditions, then you can assume ideal gas behavior, okay? Okay, so you'll probably have a homework problem on that to help reinforce that concept for y'all. Okay, so now that we've made this assessment that you can basically assume ideal gas behavior. By the way, look at that! I learned a new trick, huh? So now that we've got this idea about what an ideal gas is and how we can make an assessment if we can assume ideal gas behavior. Now what do we do? Like what is the actual nitty-gritty details of ideal gases? Okay, well, ideal gases all follow the same behavior when it comes to the relationship of pressure, temperature, and specific volume, right? So ideal gases follow a consistent behavior in terms of their pressure, temperature, and volume relationships. And I am willing to bet on this weekend's game against NC State that y'all know what this relationship is. You have all seen it before in your chemistry classes. That relationship is as follows. Pressure times volume is equal to the number of moles in the system times the universal gas constant times temperature. PivNerd, right? So that's the relationship. This equation, and we're going to talk about this equation in just a moment because it has a special name for it. Not PV equals nRT, but just the general equation that relates properties has a special name. We'll get to that in just a moment. But this equation tells us exactly how everything will behave if we know two of the three properties. So if I know pressure and volume, right, and I know the size of my system, say the number of moles, universal gas constant is constant, doesn't matter what doesn't matter what substance I am or anything like that. It's always the same number times, then I can determine what the temperature behavior will be. Okay, so that's a very important relationship. And of course, you all know that PV equals nRT is the construction of basically two major researchers' work, Boyle, right, Boyle's law, and then Henry, of course, Henry's law. Okay, so the combination of their two discoveries is what the ideal gas equation combines. Okay, so what's so special about this equation, or the general form of this equation, right? So the ideal gas equation fits the general description of what we call an equation of state. Okay, equation of state. So what is an equation of state? An equation of state is one which relates certain properties to one another. So the ideal gas equation of state relates pressure, volume, and temperature to each other, right? Okay, so now the equation of state, that's an important concept, okay? So hint, hint, hint. You want to know what the definition of the equation of state is come Thursday, okay? So the ideal gas is what we call an equation of state. That's an important thing for us, and we'll use that. We'll use, of course, the ideal gas equation of state pretty consistently throughout the semester. There are several other equation of states that exist. Okay, things like the van der Waals equations and several other things. And they're described in your textbook. We're not going to get into them this semester. Okay, again, that's more of an advanced concept. You'll very rarely ever use them in practice, and so I don't want to spend lecture time on them. If you're curious to learn more about them, come see me, or take our graduate level thermal class, of course. But for 315, we don't need to get into that. Okay, so we have this expression PV equals nRT, right? And I'm like I say, I'm willing to bet on this Saturday's game that y'all have used this equation at least at some point in your life. Now, this form of the equation, the ideal gas equation, is not very useful to us, and the reason why is because it depends on this quantity here, the number of moles, right? We don't ever, I mean, think about what we've talked about so far this semester. We've never said, how many moles are in this system. We always say how much mass does this system have, right? What's the mass of the system? As engineers, we invariably think more in terms of mass as opposed to moles. Unless you're a chemical engineer, they don't take this class, so they don't count. I'm just kidding. Anyway, so we need to rewrite the ideal gas equation in terms of parameters that we do use, which would be mass, okay? So what we do is we use the following form, right? So we often use a different form. It's still the same relationship. Use a different form of the ideal gas equation. That is in terms of mass instead of moles. Okay, and so the way that we write that different form is as follows. We have pressure, which is unchanged, volume, which is unchanged, is equal to the mass of the system, not the number of moles, the mass, times that substance's gas constant. Now this is very, you have to be very careful here. Notice that I don't write the bar over the letter R here, right? The bar is written over the letter R here, okay? But it is not written over the R that's in this form, right? There's no R here, or there's no bar here, excuse me. That's what we call the specific gas constant. And I'll talk about that more in just a moment. Then, of course, we still have temperature, which is unchanged, okay? Okay, so let me just go ahead and define some of these properties for you. Or actually, before I do that, excuse me, let me just say that, you know, note well, right? That's what that nota bene, NB, is Latin for note well, that the R is the specific gas constant, not the universal gas constant. And what's important to note here is that its value depends on the gas being studied. Okay? And you'll be able to look that up in tables to find out what those values are, and I'll talk about that in just a moment. By the way, I didn't do this very well up above here. Let me fix this real quickly. You know, we had talked about the reduced pressure and reduced temperature, right? And these are, of course, these are both defined in terms of the critical temperature and the critical pressure. And you know, I didn't say where you can find those values. So let me just say that for you real quickly, right? So T critical and P critical can be found I have to look up the table. Okay, can be found in table A1. For various substances, and actually more precisely various gases. Okay. Coincidentally, the gas constant is also listed in table A1, but there will likely be other tables that you can use to find that as well. Okay, so T critical and P critical can be found in table A1 for various gases. And so now let me just return back down to here so that we can finish our discussion. Right, the R value, the R that is the specific gas constant, not the universal gas constant. Its value depends on the gas being studied. And like I said, we'll talk about where we can. Well, in fact, actually, it is table A1, so it's the same table. So I'll just go ahead and say that we can determine R values are listed in table A1. Okay. Okay, so now let's, we're still not done fully analyzing our equation here, right? We want to go through and define what the various variables are in that equation, right? I mean, you know that PV and T are pressure, volume, and temperature, and R is the gas constant. But let's just go ahead and provide some more definition to that. So we'll go ahead and go to the next page. I need to move this fellow back up to the top here. Okay, so what we can do is we can make a nice little table, right? So we'll have our variable and a description. And the English units that you'll want to use when using this equation, and then the metric units that you will want to use when using this equation. Okay, so our first variable is, of course, pressure. And the English units that you're going to want pressure to be in are PSIA, right? So again, that A stands for absolute as opposed to gauge. And the metric units that you're going to want to use are kPa. Okay, if you have pressure in either PSIA or kPa, and you follow these other units that I'll prescribe for you, then you'll never go wrong when using the ideal gas equation. The next variable of interest, of course, is volume. Okay, now this is, of course, the total volume, not the specific volume, but we will write the ideal gas equation in terms of specific volume in just a moment. And the units on this, of course, will be cubic feet for the English units. And then for the metric units will be cubic meter. Okay. And then, of course, on the right-hand side then we have the mass. And for the English units, we'll want mass to be in pound mass. And the metric units, we'll want the mass to be in kilograms. And then we have the gas, the specific gas constant, R. Okay, so we call this the specific gas constant. And to be honest with you, I'm going to get sloppy as the semester goes along, and I'll just call it the gas constant. The rule of thumb to know is that we never use the universal gas constant unless I specifically, I'll go out of my way to say universal gas constant, since we invariably will always use the gas constant this semester. Okay, now this is where we need to pay real close attention. For the gas constant, R, we want the units to be in PSIA, cubic feet per pound mass Rankine. You're going to notice that this is going to take a departure from the English units. I'm going to put a star here because I have a note about that, which I'm going to get to in just a moment. For the metric units, the units will be kilojoules per kilogram Kelvin. Okay. Now you'll notice that the metric units has units of energy in the numerator, and the English units have this PSIA cubic feet in the numerator. That, believe it or not, is an energy unit. PSIA cubic feet is also an energy unit. The reason why we write the gas constant in metric units in terms of kilojoules is because a kPa cubic meter is equal to a kilojoule. But a PSIA cubic foot is not equal to 1 BTU. Okay, so let me just go ahead and write this over here as an aside for you. A kPa cubic meter is equal to 1 kilojoule. It's a one-to-one conversion. That's why everybody loves metric so much in the scientific community. All of these conversions are always one-to-one, right? But a PSIA cubic foot, it is an energy unit, but it is not precisely 1 BTU. Okay, and in fact, you can look in your conversion factor in the back of your book, and you'll notice, in fact, that a PSIA, so if you look under energy, you'll notice that a PSIA cubic foot, so that, just to be completely rigorous here, we basically, that conversion is the following: 1 BTU is equal to 5.40395 PSIA cubic feet. Okay, so it's, again, it's not one-to-one. Nothing in the English system is ever one-to-one, okay? like it is in the metric system. And so, which is not a problem, it's just we have to remember this and always remember to rely upon our conversion factors when dealing with English units. Okay, so then the last variable to point out, of course, is temperature, and very, very important, right? You need to use absolute values for temperature. Even though we like to think in terms of Celsius and Fahrenheit, that's going to run into problems if you use that in the ideal gas law. So in the English units, you'll want to use Rankine. That's the absolute unit for temperature, and then in the metric units, you'll want to use Kelvin. Okay. Okay. So what is this star that I identified here? What's what's so special about, or what do we need to know about the gas constant values? So you remember that you can look up the gas constant values in table A1. Okay. Now table A1E, the English units, lists R values with 2 units. Okay. The first type is the form that we need for the ideal gas equation, PSIA cubic feet per pound mass Rankine. And then the second type is going to be used when we're actually doing energy equations, right? So the other form is in the look-alike, or the consistent form that we have with the metric system, right? BTU per pound mass Rankine, okay? And you'll notice that the values are different depending on the units. And the reason why the values are different depending on the units is because that conversion is not one-to-one, right? So the values that are listed for the BTU per pound mass Rankine have already imposed this conversion factor on those values so that you don't have to do it yourself. It basically takes that step out. Okay, so now you'll notice. So if we go back to our ideal gas equation, right? So if we take a look here and go back to our ideal gas equation, we look at this for a moment. We know that we've already established that PV equals MRT, right? But this is on an extensive basis, right? Remember the difference between extensive and intensive, okay? This is written on an extensive basis. We would like it to be written on an intensive basis. So that's very easy to do. All we need to do to write this on an intensive basis is to divide this side by mass and to divide this side by mass. Here, of course, the mass cancels, right? And just recall that the specific volume is the total volume, big V, divided by the mass. And so now we can write our ideal gas equation in terms of intensive properties, which is still pressure, but now times specific volume is equal to the gas constant R times T. Okay? And so this is the form of the expression that we're probably going to use very consistently throughout the semester. Okay? This is an important one to remember, and this is also an important concept to know. Okay, so hint, hint. Okay, so let's go ahead and do an example, just so that we can kind of get a flavor for how we use these different values and things like that. And so the example is as follows. What we have is we need to calculate the specific volume of air at 32 Fahrenheit and 7 psia. Okay. So that's actually less than atmospheric pressure, right? Atmospheric pressure is roughly 14 psia. So we're and I started this lecture off by asking the question if air can be assumed as an ideal gas, the air that we breathe. The answer is yes, right? The air that we breathe is a relatively low dense gas, and so it absolutely can be modeled as an ideal gas. 32 degrees Fahrenheit, well, that's, you know, there are places in even this country that get that cold, right? But 7 psi is half of atmospheric pressure, so it's even a lower density than say atmospheric pressure. And so, you know, we can basically make the assumption that this is certainly an ideal gas. And again, if you're wondering, well, geez, I wish I knew how I could reason through that, go ahead and calculate TR and PR and see what the values are, and you'll see that they correspond to where we can make the ideal gas assumption by satisfying one of those two criteria of the rule of thumb. Okay, so we need to calculate the specific volume of this, you know, temperature and pressure. So the way that we do that is we just use the ideal gas equation, right? PV equals RT, and so I can just algebraically manipulate this as specific volume is equal to RT divided by P, okay? And now I can basically go to my table A1E. I need to look up what that R value is. I know that I was given the temperature and the pressure, so I just need to look up the R value. So I can go to table A1E, and I'll find that that's an E. In case, let me fix that for you. Okay, and actually it's table A-1E, so it's like this, table 1E. There we go. Okay. So I can go to table A1E and I can look up that R value for air. The R value for air is, and again, remember the units that I want to, you know, there's two values I can look up. So I'm going to look up the one that has PSIA cubic feet per pound mass Rankine units. So this is 0.3704 PSIA cubic feet per pound mass Rankine. So now I have all the information I need to calculate this. So specific volume is my gas constant, 0.3704 PSIA cubic feet per pound mass Rankine, times my temperature, 32 degrees Fahrenheit. Do I just leave it like that? No, I don't. You're right. I have to convert it to Rankine. So plus 459.67, right? Remember that to go from Fahrenheit to Rankine, I add 459.67. If you don't memorize that, then just look in your conversion factor. It's listed in the back of the book for your conversion factor. So this has units of Rankine. And this is all divided by pressure, which is 7 psia. And so when I plug this into my calculator, I get that the answer is 26 cubic feet per pound mass. Okay? Okay, so you may look at that and say that number doesn't mean anything to me at all, which, you know, I can certainly value that. Remember that specific volume is the inverse of density, right? So if you were to inverse 1 over 26, you'd have a number that's less than 1, right? So that gives you an idea, considering the fact that water's density is, say, 64 pound mass per cubic feet, right? And the density of air is well, it's not just less than 1, it's actually less than 0.1. That gives you an idea of how much lower density air is than water, for example. Okay, so now you know, now that we've kind of talked about ideal gases and how we manipulate them, you know, it might also be helpful for you to know what are some of the common substances that we're likely always going to be able to treat as ideal gases, right? And so these are basically the following. So common ideal gases that we'll use are, you know, first of all, air, right? So if you see air, assume it's an ideal gas, right? You're going to be able to assume air is an ideal gas. Carbon dioxide, right? That can typically be treated as an ideal gas, unless you're dealing with compressed carbon dioxide, in which case you start to get into real gas behavior. I throw that caveat in there because, again, I know a lot of you are going to work for the oil and gas industry someday, and so you need to be aware of some of the real gas behavior situations that you'll run into with various substances. Argon, the same thing. Generally speaking, it's an ideal gas unless you're compressing it. Nitrogen, right? Unless it's liquid nitrogen, then you can't assume it's liquid is not a gas, so it's not going to behave as an ideal gas. And oxygen, O2. Okay, so now we have the ideal gas relationship that allows us to do, for example, the relationship among pressure, temperature, and volume. But if you remember when we studied the phase change substances like water and R134A, we were finding more than just specific volume, temperature, and pressure. We were also finding internal energy, we were finding enthalpy, and we were finding entropy. Okay. Now, in the case of ideal gases, we can't go to a table. There are so many ideal gas, right? Just look at this list here. There's six different gases, right? So we can't create a table for every single substance. It's just not practical. But fortunately, their behavior, their energy behavior, their entropy behavior is consistent so long as they're behaving as an ideal gas. And so what we do, rather than finding, say, the energy of the gas at a state, like we would with water or R134A, we would find the change in energy of the gas as it undergoes a process. And the same is also true for entropy. We will find the change in entropy of that ideal gas as it undergoes a process. And so we do that as follows, right? So we can determine the change in energy, okay, of an ideal gas. And that basically looks as follows. Oops, sorry. We can say that the change in internal energy, delta U, of an ideal gas is equal to the constant volume specific heat. Remember, that was one of the properties that we listed in that big table of properties, actually the last online lecture that we did. The constant volume specific heat, okay, times the change in temperature, delta T, okay. Now, we're going to box this, and we're going to say for right now, just know about it, okay? But I'll actually show you the derivation, the development of this equation later on this semester. We're not quite ready to do that right now, but later on this semester we will be able to get to it. But that'll of course come later on this semester. Okay. Okay, so that's how you determine the change in internal energy of an ideal gas, and just so that we're clear on all of this information, CV is what we call the constant volume specific heat. And you can find the constant volume specific heats in table A2, I believe. Just a moment. Let me look this up. Yes, table A2 is where the various specific heat values are listed for different substances. So this is table A2. Table A2 and table A2E. Okay. Okay, so we don't just have the change in energy of an ideal gas, we also have the change in enthalpy of an ideal gas, right? And so we can go ahead and take care of how we do that. And so the change in enthalpy of an ideal gas The equation that we use for that is as follows. Delta H of an ideal gas is equal to the constant pressure specific heat, not constant volume, the constant pressure specific heat, times the change in temperature, delta T. And again, Cp is the constant pressure specific, and we will be able to find those values just like Cv in table A2. Table A2 and table A2E. Okay, and then the final thing that we need to know how to calculate is, of course, the change in entropy of an ideal gas. So the change in entropy we actually have two equations that we can use. Okay, the first, and the choice of equation that you use depends solely on the information that is available to you. That's it. Okay, so the first depends on if you have, for example, the specific volume. Okay, the specific volumes of the substances. So the change in entropy of an ideal gas is equal to the constant volume specific heat times the natural log of the temperature at state 2 of the gas divided by the temperature at state 1 of the ideal gas plus the gas constant R times the natural log of the specific volume at state 2 divided by the specific volume at state 1. The second form that you can use, and again, it all depends on what data you have available to you, is as follows. You use now the constant pressure specific heat times the natural log of T2 over T1, temperature of the gas at state 2 divided by the temperature of the gas at state 1. Caution, caution, caution. Make sure that you're using absolute temperatures there. Whenever you do a ratio of temperatures, you have to use the ratio of temperatures, okay? Minus the gas constant times the natural log of the pressure at state 2 divided by the pressure at state 1. Okay? Okay, so, and again, we will talk about how we develop these equations later on this semester. We have to learn a little bit more about system analysis before we can actually apply that information to developing these equations. But for right now, I want you to be able to calculate the change in energy, change in enthalpy, and the change in entropy of ideal gases. And so those are those expressions there. Okay, so now that's basically everything that we need to know about ideal gases so far this semester. The next piece of information that I want us to go over are just basically some final pieces of information, some final concepts that are very important for us in terms of thermodynamic systems, okay? And the first concept is what we call the state postulate, okay? So what is the state postulate? The state postulate basically formalizes something that we've been doing so far. We've talked about it already, but we haven't necessarily formalized it in a statement. You notice that whenever we find properties, all you need to be given are two properties. That's it. If you know two properties of your system, you can use those two properties to look up every other property in the system. That's called the state postulate, okay? So, or that's what the state postulate basically stipulates. The state postulate says that you can have, or you need no less and no more. So you will only ever need exactly two. No less and no more than two independent and intensive properties. To fix the state of the system. So what do we mean by this word or this phrase, fix the state? Well, fix the state means that if I fix the state, it means I know the state of my system. And if I know the state of my system, then I can determine all the properties of that system at that state. If I know what my state is, I know everything about that state. I know everything about that system. Okay. And oops, I put a period here. Let's hold off on putting a period here. There is some additional caveat information, right? So of a system composed of a pure system. Excuse me, of a pure substance, not a pure system. Okay. So there are situations, in fact, when you need to have more than two properties. We won't ever need to have more than two properties this semester. But again, working out in industry, if you're in the oil and gas industry, or if you are, say, in my field doing IC engine research, and you have chemical reactions, you may need, in fact, more than two properties to fix the state of your system. Okay, but that's something that you would acquire knowledge of as you started working in the field. But for all of our simple systems composed of pure substances, you only need two independent properties. Okay, so what is a pure substance? It's basically one which is characteristically uniform, characteristically the same, in its properties. Oops. And behavior. That's a V. Okay. So all of the substances that we're basically dealing with this semester, fortunately, are pure substances. So for example, a pure substance would be water, right? It's if I have a bucket of water, it's water everywhere throughout, right? Its characteristics are the same everywhere throughout. Its behavior will be the same everywhere throughout. R134A, right, is a pure substance. Air, for our purposes, can be studied as a pure substance. So again, you may be thinking, well, air is composed of oxygen and nitrogen and all these other trace species. Wouldn't these different molecules behave differently? Yes, they would if you were looking at the substance on the micro scale. But since, if we have a box of air and we're looking at it macroscopically from a big scale, it basically all behaves the same. Okay, the state postulate, that's an important one. That's an important concept. Okay. Okay, so now the other important concept that we need to describe pretty well this semester is the idea of equilibrium. Okay, in fact, actually, guess what? Equilibrium is incredibly important. Okay, so this is a big one. This is a big concept. Okay. Okay, so we'll wrap up today's lecture basically talking about what equilibrium is and why it's important for us. So first of all, let's go ahead and provide a definition for what equilibrium is. I know all of you have heard the word before, but let's just go ahead and provide a definition for it. Okay, so equilibrium is a condition when all internal gradients are equal to 0. Okay. Another way to interpret this, so if I were actually in class right now and I asked you all to provide a definition for equilibrium, I can probably promise you that one of you would say balance, right? So another way to interpret equilibrium is to say the system is balanced. It's not the most rigorous or precise definition, but conceptually I can see how it helps us understand what equilibrium is. Oops, I've gone off my screen just a moment. I'll fix that for y'all. Okay. Okay, so now equilibrium is a hugely important concept for us in thermodynamics. Okay, and so we need to know how we know if a system is in what we call thermodynamic equilibrium. So for a system to have thermodynamic equilibrium, there must be met four conditions. I realize that's a little Yoda speak, but that's just how it came out. Okay, there must be met four conditions. What are these four conditions? Well, you first of all have to have thermal equilibrium. Okay, I shouldn't say first of all. I mean, it doesn't. There is no order in which these are met. It's just your system has to be in thermal equilibrium. Okay. Secondly, you have to be in mechanical equilibrium. Thirdly, you have to be in phase equilibrium. And fourth, you have to be in species equilibrium. Okay, so what do all of these mean? Well, if you are in thermal equilibrium, it means there are no internal temperature gradients, right? Remember, equilibrium is you have no internal gradients. So if you are in thermal equilibrium, that means that there are no internal temperature gradients. And if you have mechanical equilibrium, that means you have no internal pressure gradients. If you are in phase equilibrium, it means you have no internal phase gradients. That doesn't mean that you can't have the substance have more than one phase. It would mean, so for example, you could have water that is, two-phase, liquid and vapor, but they're liquid and vapor at the same same phase point, right? In other words, they're at the same temperature and pressure essentially. It's almost a duplication, in fact, of saying that you have thermal and mechanical equilibrium. And then you have, of course, species equilibrium. And that simply means that you have no internal concentration gradients. So if you had, oops, I'm sorry, I just realized that I miswrote this. I'll fix that in just a moment. No internal concentration gradients. So if you had, for example, a mixture of nitrogen and oxygen, for example, there isn't a region in the system where there's relatively more nitrogen, a concentration or an excess of nitrogen than elsewhere in that system. Okay, so in other words, it's uniform and homogeneous throughout. Okay. Okay, so again, this may or may not be too terribly helpful at this point. So let's draw a diagram that looks at what a system would be not in phase equilibrium, or not in, excuse me, not in equilibrium. And let's suppose that our system is has a mechanical gradient. Okay, so consider a system not in mechanical equilibrium. What does that look like? Okay, well, let's see. We've got our system here. Okay, and let's suppose that we have mechanical non-equilibrium. So for whatever reason, all the particles of this system, right, or most of the particles of this system have congregated over on this half of the system, right? So there's a higher concentration of particles on this side of the system than on this side of the system, right? In other words, it's very, very dense on the one side, but rather sparse on the other side. Such that if I were to take a pressure measurement, right, if I were to stick a probe in there and take a pressure measurement, and I call that P1, okay, and then I were to take a probe and I were to stick a pressure measurement there, and I were to call that P2, okay, obviously P1 would be greater than P2, right? That's a mechanical non-equilibrium. That's a mechanical gradient. There's a gradient there such that the tendency, what's the tendency of this mechanical non-equilibrium? The tendency is that the particles are going to flow in this direction, right? In other words, you're going to have the high concentration particles. There's a mechanical gradient there. They're going to have a tendency to flow to where there's a lower gradient. Second law principle, ladies and gentlemen, second law principle. And so what happens after a period of time, right? So after a period of time, my system now looks like this. My particles are now all uniformly distributed throughout the whole system. The natural tendency is for those particles, for that gradient to be eliminated, right? The natural tendency is for the particles in the high concentration area to flow to the low concentration area. So that now when I take a look at my pressure measurement and I compare these two, right? So this is still P1 and this is still P2. Now they're equal. And now I have a condition of mechanical equilibrium. Okay? Okay, so now what all this means, there's some pretty big implications here. Okay? Do you remember when I said that the natural tendency is for the particles in the high concentration to flow to the area of low concentration? And I said that that was a second law concept. In other words, that's the natural tendency. The natural flow, the natural direction of the process is to flow from high concentration to low concentration. And recall what we always do, or what always happens with natural processes. entropy is generated, right? Remember that entropy generation is only ever positive. So if I were to calculate an average entropy of this system, and let's say that, I call this S average, right? And then I were to then calculate the entropy of the system after it reached mechanical equilibrium and call that the entropy of the system, well, I generated entropy, right? So after this period of time, if from a second law perspective, this entropy generation is greater than 0. So what does that mean? The entropy of the system here is relative to this average entropy that we started out with when we had the non-equilibrium. Entropy generation can only ever be positive. So the entropy of the system here, after the process, is greater than the average entropy, right? So the entropy of the system, S system, is greater than the average entropy. Okay? And the other thing that we can say, the other important concept that we can say, is that what this entropy generation represents is it represents a lost opportunity to exploit the mechanical gradient. In other words, when I have this high concentration of particles here and this low concentration of particles here, think about this. There is a flow, there is an orderly flow from high to low because of that gradient. Orderly flow, that's high quality energy. I went from a condition of having high quality energy to a condition of having low quality energy. I could have invented some device that I stuck in between these two regions in my system that exploited that flow of energy and converted it into useful work as I went from high concentration to low concentration in that gradient. But I didn't do that. I didn't take advantage of that gradient, and the system naturally dissipated the gradient on its own. That's this concept here, that entropy generation is always greater than 0. And I now have this system of mechanical equilibrium where now I have a lower quality energy. I no longer have that gradient. I no longer have something that I could exploit into doing useful work. Okay? That is a fundamental, critical concept that we're going to continue to hone and continue to reinforce all semester long. This idea of lost opportunity to do work. I have a more ordered system here than I do here. That's why my entropy of this system is greater than the entropy of this system, which is written in this statement right here. Okay? And of course, we know that the second law concept says that my gradient will go from high concentration to low concentration. What would be impossible is if I started with this system here, right, and somehow spontaneously a high concentration of particles formed over here, leaving a low concentration of particles over here. That's impossible. That would be the situation where now the entropy of that condition is less than the entropy of this condition here, where there's equilibrium, where there's no gradients. That would mean negative entropy generation, and that's what's impossible. That natural, spontaneous ordering of energy, that is impossible. Okay? The natural tendency is for things to go from high quality energy to low quality energy. Okay, so I know I'm over time here, but there's one last concept that I need to do for you, and that is to define what a state is. So now that we know what equilibrium is, we can now provide a more rigorous definition for what a state is. Actually, I think I can do this on the next page here. Yes, I can. Okay, so let me do that. I'll just go on the next page. I know that your time is precious. Okay, so let's go ahead now and define what a state is. Okay, assuming thermal, phase, mechanical, and species equilibrium we could then say the system is in thermodynamic equilibrium and when my system is in thermodynamic equilibrium, it exists at a state. So a thermodynamic system is at a state when it's in thermodynamic equilibrium. That is the definition of a state, a system that is in thermodynamic equilibrium. No internal gradients. We can use single sets of properties to characterize the entire system, and therefore exists at a state. Okay? And that is a very important concept, ladies and gentlemen. We want to make sure that we have that certainly reinforced. Okay? Okay, very good. So we're over time, so I'll just very quickly summarize what the important concepts are, right? So our important concepts, of course, are ideal gases. We talked quite a bit about ideal gases, how we define them, how we know if they're an ideal gas or not, what the ideal gas equation is. Okay, so there's actually several concepts that are embedded in that. We came up with, okay, so let me just do this. So the definition is an important concept. You know, what is an ideal gas? Or you know, assuming, maybe a better way to say this is assuming ideal gas behavior. And the ideal gas equation. And then finally, the changes in energy, enthalpy, and entropy of ideal gases are all important concepts. Secondly, we talked about the state postulate, very important. No more or no less than two independent properties to fix the state of the system. And then finally, we talked about equilibrium, very important concept. Okay, ladies and gentlemen, I do apologize for going over, but thank you very much for your attention. If you have any questions, please feel free to contact me by email. Otherwise, I'll look forward to seeing you Thursday, September 27th. Bye-bye.